All right. Hello, everybody. It's Thursday on this side of the video. I hope everybody's safe. This hurricane's been pretty rough on the upstate, and I know a lot of us are still without power. I do have power. Thank goodness we got it back. Um, and I know that you guys, a lot of us have been worried and all right, let's try this again. All right, this is Thursday on this side of the video. I'm getting this prep for next week. I hope everybody's safe and everybody's doing well. I know this hurricane was devastating for a lot of people, and power is still being restored. Internet still being restored. So I hope you all are doing well. Today we're going to be starting Unit 4, and we're going to begin with looking at the layers of the atmosphere. What we've been studying is interior Earth, and now we're taking a look at exterior, what's happening above the surface, rather than just what's happening below. And a lot of these concepts are the same, and that's why we really worked very hard in Unit 3. I expressed to you quite often in Unit 3 how those concepts are intricately tied to everything else that we do, and you're going to really get to see that starting in Unit 4. We have lots of new standards. I know y'all are super excited to not see 2-1 again, but we have 2-2, analyzing data to make the claim that one change on Earth's surface can create feedback that causes change in other systems. Develop model based on Earth's interior that describes cycling of matter through convection processes, and maybe not so much the interior. I could probably take that one out, but it's more of cycling of matter through convection. That's still important to us when we discuss weather and heat differentials. And then 2-4, a model to describe how causes of short, long-term variations of energy flowing into Earth systems create change in climate. That's going to be important as we move into weather. And then investigate the ways water, given its unique physical chemical properties, impacts various Earth systems. So we're really talking about the interaction between the hydrosphere, which is water, and then which you should have learned in your lesson from the start of the week, and also our atmosphere, okay, which is the air and the spheres that are above Earth's surface. So the interaction between the hydrosphere and the atmosphere is incredibly important as we move further into weather. All right, what do you need to know? Some high points here. I'm gonna make it pretty quick today. This one's pretty seamless, and the information you should have a good foundation in already before coming to high school Earth science. But high points here: the atmosphere is not just oxygen, right? We know that. There's lots of gases that surround the Earth, and the majority of which is nitrogen, right? There's some oxygen, um, and then just a little bit of carbon dioxide, right? And it makes up about 1 to 2% of the radius of Earth. It's like its protective skin. You're going to find out, boy, you thought interior Earth was, when we talked about all that stuff, how fickle our existence is. When we talk about the atmosphere, you're going to be really surprised at just how perfect our little Earth is in the great scheme of things to keep human beings alive. But it interacts. You need to know that. That's really important. It interacts with other systems. Again, it just talks about the hydrosphere, the geosphere being Earth, the interior Earth, which we've already studied, and then the ice caps as well. The Earth's atmosphere begins at the surface. There is no, we're going to talk about pauses, but there's no like defined definition or end to each of these layers. They kind of just mix into one another and until they fade away into space. Here, gases: nitrogen 78%, oxygen 21%, and then the other gases about 1%. And you can see that for yourself. But most kids are pretty surprised to find out that nitrogen is the majority of our atmosphere. 99% of the atmosphere, what that means is, that wording is a little bit confusing. What that means is like the molecules themselves, how compact the atmosphere is, lies within about 50 kilometers of the surface. And that makes sense. We'll get to that in a second, but gravitational pull, right? Earth's gravitational pull As we get further away from the surface, it becomes less and less, so that those gases then become lighter and lighter. And so that's what that means. The bulk of the atmosphere lies within 50 kilometers of the surface. Here are the layers. This would be, for my kiddos, you want to screenshot this. Make sure that you put this into your Unit 4 folder as your study guide. The troposphere is the very first sphere. That's where we are. That's where weather occurs. Some travel occurs there. We're talking about planes between the troposphere and the stratosphere, right? So that's about 10 kilometers from the surface, and it is the thickest. Again, going back to what I just said just a minute ago, 99% lies within that 50-kilometer range. It's the thickest layer. And that makes sense, right? We talked about density in interior Earth. What happens to dense materials, right? It sinks. So if we were using that same concept to understand the atmosphere, it would make sense that closer to the surface would be the thickest layer. This is where humans live, and also, again, weather occurs in the troposphere. Then we have the stratosphere. The stratosphere is where those big jets fly, altitudes of about 10 to 48 kilometers. And one piece of information that you really need to own for the stratosphere is that this is where the ozone layer is located. We've talked a little bit about the ozone layer, and you've probably heard it maybe if you took environmental science. I know that in 6th, 7th, 8th grade, middle school sciences, they discuss this concept of the ozone layer, but we're going to touch on that a lot more here in this class. Then we have the meso, just like Mesozoic was the middle era in the GTS. Meso still means middle. It's the one that's directly smack dab in the middle, the mesosphere. Meso means middle. 50 to 80 kilometers. This is where meteors burn up typically. If it makes it through that mesosphere, again, I love space. We're going to get, that's all that yummy stuff is Unit 5, Unit 6. But the mesosphere is where the meteors burn up in our atmosphere. It's good, right? Because that's one safe place or thing that is keeping us from getting really hit by a lot of meteors. If it makes it through the mesosphere, it's very likely that it will become a meteorite and strike the planet. So thankful for the mesosphere. And then we have the thermosphere, thermo meaning heat, right? Gases are very sparse here. That's 80 to 140 kilometers. High energy particles, and this is where we have the ionization of gases, that solar radiation. I'll talk about it a little bit more in just a minute, but the solar radiation here is really broken apart, and we get these ions or high energy particles, and this is really cool. Well, we're not going to get into mostly the ionosphere, but anyway, this is where a lot of communication travels, like our radio waves and things like that. Then we have the exosphere. The exo, exit, exo, is the outermost layer, and it doesn't really, again, we don't really have a definite start or finish to the exosphere. It's just kind of where, okay, Earth's atmosphere fades. It fades on into space. Please watch that in the self-paced videos, or self-paced Nearpod. It's very good. Separating each layer, I hesitate to even use that word boundary because there's no real boundary. There's just a mixing of the gas in these places. But we have what's called a pulse. So between the troposphere and the stratosphere, we have the triple pulse. Again, the stratopulse between the stratosphere and the mesosphere. And so that makes sense, right? From one going into the other. Use the same root work there, and we're adding pulse to the end of it. So it's just that boundary in between where those gases are mixing and becoming the next layer. Air pressure and density are easy concepts here. I am going to touch on this, but these are very intuitive. Okay, Earth's gravitational pull, Earth's gravity, its control over molecules is going to be greater at its surface. That makes sense, right? So as we get further away, Earth's gravitational pull is less and less and less, and therefore that air pressure is less and less and less. So as we move away from the surface, right, air pressure decreases. As we move away from the surface, air pressure decreases. One reason for this, well, I guess one reason for density doing the same as it does in interior Earth is because of this air pressure, because the air pressure at the surface is bringing those molecules together and making them so tightly packed that the air itself is denser. And so just like with interior Earth, all right, as we go towards the surface, as altitude decreases, as we get closer to the surface, that's where we have the denser gases, the denser air molecules. Okay. So air pressure and density, they're friends. They do the same thing. Air pressure and density do the same thing. As we get closer to the surface, they increase, or as we move away, both of them decrease. This is something you may want to screenshot, put in your U4 folder. This definitely is screenshot worthy right here. All right, this one's huge. Temperature does not do the same thing, and this one kind of throws kids for a loop because we just studied interior Earth, right? And we discussed in interior Earth, as we dig deeper or as we go deeper into the layers, it gets hotter. Okay, density increases, pressure increases, and those two things are the same as interior Earth, but temperature is not. All right, it is way more complex and has to do with the composition of these layers and when solar radiation rather than just its consistency and its heat source. Okay, so let's get started with that. Troposphere, as we move away from Earth's surface, the troposphere, within the troposphere, um, as elevation increases, let me say that, temperature drops. So as we move away from the surface, temperature drops. And that makes sense, right? As we get further away, it would get colder. But then we have this crazy phenomenon here in the stratosphere. In the stratosphere, temperature actually increases, and we call this a heat inversion. All right, so we have this colder mass that's being trapped by this warmer layer on top. Why is that? Because in this layer, we have what's called the ozone. And what the ozone does is it breaks apart, absorbs and breaks apart ultraviolet radiation, that UV radiation that we need protection from is actually absorbed in this region, which then intuitively would mean that it's getting hotter. Okay, so if it's absorbing UV radiation, it's going to be hotter, and we are thankful that the ozone absorbs as much solar radiation as it does. Okay, in the mesosphere, we have another drop. All right, mesosphere in the middle, that temperature drops again. All right, there's no ultraviolet radiation being absorbed here, and so the temperature drops again. And then we have another phenomenon in the thermosphere where temperature increases again because of the ionosphere, which we're not going to focus on as much. But the ionization of those molecules by solar radiation causes the temperatures to increase in the thermosphere as well. And if you have trouble with that, just remember it alternates. Okay, cooler, hotter, cooler, hotter. All right. Also, there's some key things here like thermo. Thermo means heat, right? Could mean a lack of, could mean more of. Just like you wear thermals in the winter to keep yourself warm, or thermal cameras identify heat signatures, right? A lack thereof or more. So that prefix there is really important. If you just kind of identify that one and you're like, oh, that means that one's hot. I remember that one's hot. Okay. And then you can get the rest of them from there because they alternate. So we do have this alternating pattern, which is super cool. Again, kids get this really mixed up, or they miss questions because they think they're going back to thinking of layers of the earth. But this part, the temperature is very different. Pressure and density are not, but air temperature is, and they alternate. Okay. Again, this is the temperature inversion I was just talking about when you have that warm air mass that is located above a cold air mass. This is huge for weather. All right, but I slipped it in here because if we can get talking about this already, then when we get to weather, you're going to be like, oh, I remember that. So that's why that's in there. The consequence of these inversions is convection. I told you we were going to get to it again. So weather, again, this is your tie into weather here. Convection is that airflow, high pressure to low pressure. Warm air is less dense. Cool air is not. And so we have this heating, rising, and cooling and falling of material. And this happens within our atmosphere as well, especially within the troposphere. That convection is what creates weather. Composition, again, we talked about density. We talked about composition of interior Earth's layers. So a lot of these are the same concepts as we're moving into the atmosphere, but this is particularly important. What's happening within within each of these layers. So below the thermosphere, so you have the troposphere, the stratosphere, the mesosphere. All right. The air currents, going back to that convection I just talked about right there, the air currents, due to the inversions, temperature inversions, mix the gases thoroughly. And we call that uniform, right? It's a uniform solution um, called the homosphere. So below the thermosphere is the homosphere. Again, just another word, but what that means is that it's all the same, right? All those gases are mixing. It is uniform. Beyond the thermosphere and beyond the ionosphere, right? They're heterospheres, which means that these gases are not going to mix. There's the atmosphere in this location is so thin that there is no convection occurring there. And so your heavier gases like nitrogen and oxygen are going to sink. They're going to be towards the bottom. And your lighter gases like hydrogen and helium are going to be at the top. And this is non-uniform. This region is called the heterosphere. Weather occurs in the troposphere is so important moving forward. This is so key right here. This next sentence. Interaction between the atmosphere and the hydrosphere is what we get with weather. The interaction between the water that is here on Earth and the layers of the atmosphere gives us the water cycle. And that is so key when we're talking about the weather, which occurs in the troposphere. Beyond what we're talking about today, we really kind of leave mesosphere and thermosphere and ionosphere. We kind of just leave it here. And we really focus more on what's happening with the weather within that troposphere and that convection, that temperature inversion and what it causes, more about how it affects us here on the surface. The stratosphere, you need to know it contains the ozone. I think that's the second time I've said that. That's super important. Contains the ozone. Is essential to life. It absorbs UV radiation and actually allows us to survive here on Earth. Without this, we would not be able to exist in the manner in which we do. Okay, I know you've heard of Earth. Earth is in like this beautiful Goldilocks zone, is what they call it, third planet from the sun. We're just close enough to where we get the heat that we need, and we get the effects of solar radiation, for example, photosynthesis of our plants and things like that, where life can survive. We are at that exact place where any closer, it would really affect our water. It would really affect radiation here on Earth. Any further away, that would affect our temperatures to the point where it would be uninhabitable. But this perfect little Goldilocks zone that we're in still isn't good enough because the sun is so powerful. The ozone layer of Earth is primarily responsible for absorbing that solar radiation. The thermosphere is responsible for reflecting that solar radiation, so that only about 2% of the solar radiation that we experience, or our exterior Earth experiences, gets to us. That's crazy, right? 2%. That's insane. So between our thermosphere and the ionization of solar radiation there, and the stratosphere, where the ozone layer absorbs that UV radiation, 2% is what gets to us. And we are thankful for that, because any more or less, and we would not exist in the manner in which we do. Y'all make sure you watch that video. All right. Ionosphere, again, we're going to touch on it, and then we'll move on past that. It should really say extends. It can extend from the mesosphere, y'all, but it really should say extends from the thermosphere. It grows, it expands, and it gets smaller. And this happens every single day. It happens due to different patterns of solar radiation. It could be different if there's a solar flare, if there's more activity on the part of the sun that we are particularly facing at the time. This is really, really highly, what's the word? It varies a lot. Okay, so it could shrink, it could expand into the mesosphere. But really, what you need to know about the ionosphere is that there are a high concentration of electrically charged particles here because of the ionization of solar radiation. At night, radio signals can penetrate the ionosphere further because there's less solar energy, and they can travel great distances. So this is really big for communication purposes, especially with radio waves. All right, to summarize everything, this is a great one to screenshot as well. To summarize everything within this lesson, temperature inversions, that's, I feel like the rest of our semester together is all about temperature inversions, heat inversions, right? And that creating convection. So temperature inversions are increase in temperature with an altitude. So we have that low temperature, high temperature, low temperature, high temperature within our spheres. Major inversions occur in the stratosphere. That's where the ozone layer is, and that's where UV radiation is absorbed. UV heats up ozone, creates the inversion. Inversion subsequently seals the troposphere, which doesn't allow that vertical movement of air. Again, that it traps in that cooler air, so it holds it down because, of course, it's hotter. The movement of air interactions of the troposphere with the hydrosphere energy. This creates weather. So what do you need to know there? You need to know that the hydrosphere and the troposphere, or the hydrosphere and the atmosphere, particularly the layer called the troposphere, interacts together. It's driven by solar radiation, and this creates our weather. You're going to see that a lot. If you look at the big picture of interior Earth, right, solar radiation had nothing to do with driving interior Earth. That was heat differential, right, and convection, and those two things together, right? The atmosphere is different. Weather is different. This is the processes that we are talking about now on exterior Earth are driven solely by solar radiation. Even when we move to talking about the hydrosphere and ocean currents, again, that is driven by solar radiation, or the transfer of energy from the sun to the Earth. Besides creating the inversion, stratosphere ozone layer shields life, right? The thermosphere is responsible for breaking it down, the ionosphere, and reflecting UV radiation. What does get through then is absorbed by the stratosphere from the ozone layer, and then only about 2% of that gets to us here on Earth. So super thankful for that. And make sure that you have a screenshot of this. This is the last slide. The last one's time to climb. Make sure that you do that on your self-paced Nearpod. But I hope you enjoyed it. We are going to really get into weather and the atmosphere a lot more. Not next week, because we're doing this next week, but the week following, that will be more focused on what's happening within the troposphere and the convection and the solar radiation that's driving those processes there. All right, guys, stay safe. See you soon.